Amy Ott from Concordia College in Moorhead has shared her screen, and she will be talking about plasma physics in Python, a computational program for spectral line analysis. So Amy, I'll turn it over to you.
All right, can everyone see my screen all right? Perfect. All right, so hi, my name is Amy Ott, and last summer, I got the opportunity to work with Dr. Matthew Archmiller at Concordia College in creating a computer program in the language Python for plasma spectral analysis. So let's see here. So first, I'll give a little background information on what plasma spectroscopy is. And then I will talk about some of the mathematical models that we used in our program. Then I'll talk about the purpose of the program and give a brief outline of how the program works. And then lastly, I'll talk about how we tested the program and the results that it gave us. So before we define plasma spectroscopy, we need to look at plasma itself. Plasma is an ionized gas, meaning the electrons have separated from the nuclei, usually in atomic collisions. And a gas can be partially or fully ionized with either extreme heat or a large electric field. And plasma spectroscopy then is the study of the radiation that is emitted by excited electrons in the gas transitioning from higher energy states to lower energy states. And these transitions are measured by a spectrometer, and they create different peaks or lines in your graph. And analysis of these peaks can be used to determine physical characteristics about the plasma, such as temperature, density, and composition. So this figure shows a schematic of a spectroscopy setup that Dr. Archmiller took a few years ago of an argon plasma. The charge coupled device in the CCD detectors in a stellar net blue wave spectrometer collected photons from an argon plasma that was created using a DC glow discharge, and those photons were then turned into an electrical signal, which were then sent to a pixel array. And as charge accumulates on the pixels, it's proportional to the radiation intensity that is emitted at the atomic transitions. And so we're able to analyze these different lines in different ways, but the method that we chose for our program is curve fitting. It's one of the most common ways to analyze spectral peaks. So what that entails is using a function to fit a curve through the peaks and finding the best fit parameters, and those parameters can help us find the physical characteristics. And so we implemented two different fitting functions, the Gaussian function and the Lorentzian function, or the Cauchy-Lorentz function. The Gaussian function is most commonly seen in statistics, but it can be used to define any symmetrical bell-shaped curve. And the Lorentzian function is very similar to the Gaussian function, but it can be a better approximation for asymmetrical peaks. And so here is examples of our two fit functions fitted through the first line in an argon spectra. So as you can see, the Gaussian function on the right, the parameters in the equations are A is the amplitude of the wave or of the peak, X is the wavelength, mu is the the center of the peak, and then sigma is the distance from the center of the peak. And you can see in this case, the Gaussian fit was much closer to the original data than the Lorentzian function. The Lorentzian function has wider tails, and so it had an overestimation of the rising and the falling edge of this particular peak. And so with that background information kind of out of the way, the purpose of our program is to hopefully be incorporated into the physics curriculum at Concordia College in the future in labs that are related to plasma spectroscopy. And to make it usable for students, we had 3 main goals in mind: to have an easy way to input initial guesses for the peak's amplitude and wavelength, and we needed the program to use that input to fit a curve through the peaks and find the best fit parameters, and then to use those best fit parameters to find the uncertainties and the chi-squared statistics, or the goodness of fit of the functions, and then to save the results as a text file or print the results to the screen. And so here is a flow chart of kind of how the program works. So first we start off in the main class. The user inputs their data file with the spectra, and then the user can choose the fit function, either the Gaussian or Lorentzian function, and they can also choose whether to print the results to the screen or save it as a text file. And then when the program is run, the plot of the spectra is displayed, and the user is prompted to right-click on the top of each peak, and a left click will actually delete input points. And so those click inputs are put into an initial parameters array, and a value of 0.5 nanometers was used for the width of each peak. And so that is all sent to the fit function class, which then calculates the function for each individual peak, and then it sums them all together to get the fit function for the whole spectra. And then it calculates the best fit parameters and the covariances. And the best fit parameters with the fit function is then plotted against the original spectra, and the covariances are then sent to the error analysis class. And that class calculates the chi-squared and the reduced chi-squared statistics, which are goodness of fit of the function. And then it also calculates the uncertainties in the best fit parameters. And then all of those are then sent to the report class, which organizes all of our results so that the fit function is listed at the top, followed by the chi-squared statistics, and then it pairs the best fit parameters with their uncertainties and puts them in a list organized by peak. And then again, all of that is then either printed to the screen or saved as a text file, and then the program ends. So it's pretty quick and simple, and hopefully it will be easy to use by students in the future. And so talking a little bit about the goodness of fit, we use the chi-squared statistics as defined in John Taylor's Introduction to Error Analysis to test our goodness of fit. And these equations are what we used in our program. The n represents the number of data points, and y sub I is the original data. F of x sub I is the fit function, and the sigma is the standard deviation, or the difference between the two functions. And in the reduced chi-squared statistics, the 1 over n minus n param is the degrees of freedom, and m param is the number of parameters that we have in the fit function. And then It's just multiplied by chi-squared again. And ideally, we want the chi-squared statistic to be low and the chi-squared or the reduced chi-squared statistic to be to have a value close to 1. So there we go. So to test our program, we used a sample argon spectra that was collected by Dr. Archmiller using a setup shown at the beginning. But we expected our chi-squared statistics to be very high because our error allowance was only set to 1. So it was a very low error allowance. So we expected the goodness of fit to be very high. And our program found that the Gaussian function was a better approximation for the argon spectra than the Lorentzian, as the chi-squared statistics were lower. But the peaks were skewed towards higher wavelengths. And we had a few hypotheses as to what caused the skewness. One was some sort of instrumental error function, and another one could have been a charge accumulation time on the pixels being too high, causing a broadening effect or an overflow into adjacent pixels. But unfortunately, we couldn't test these hypotheses, so we don't know for sure what's going on. And so here is the two fit functions plotted against the argon spectra. As you can see on the right, the Gaussian fit, the chi-squared statistics are lower than the Lorentzian fit, and you can see that the here along the tails, it follows the data much closer versus the Lorentzian fit that overestimates the tails of the peaks. And so in quick summary, plasma spectroscopy is the study of radiation emitted by ionized gas that has been partially or fully ionized by either extreme heat or electric field. The mathematical models that were used were Gaussian and Lorentzian fits, and the program allows the user to input initial guesses, and it calculates the best fit parameters and uncertainties. And our test spectra was more Gaussian in shape. And so thank you to Minnesota NASA Space Grant Consortium for funding the project and allowing me to speak to you all today, and for Concordia College, and thank you to Dr. Matthew Archmiller and Dr. Luis Manzoni. And that will conclude my presentation, so I will open it up to questions that anyone has.
Great. So, Amy, I do have a question. It looks like your project was very computational heavy. Had you worked with Python before this project? And how was it? And sort of, you know, could you, if you know other languages, could you compare it to other languages and that experience?
Yeah, so this was actually my first time working with Python. We spent the first couple of weeks of the project learning Python. So it was very much a learning experience for me. I got to learn a whole new language. I did know a little bit of Java beforehand, and so it was pretty similar to Java, but I found it a lot easier to pick up than Java. I found it a lot more intuitive, and the coding process was a lot quicker than my experiences in Java.
Cool. So let's give Amy a hand with our reactions, or however is easiest for you. And Amy, if you could stop sharing your screen, and we'll ask the students from St. Kate's